Majesty, everyone! We present to you the second phase of our water rocket, namely Phoenix Blaze rocket. In this presentation, we will show you our initial plan, launching of our product, computation for the projectile, and explanation of the laws of motion applied. Now, fasten your seatbelts and let the countdown begin.
Design overview. Invest in the future of space exploration with Phoenix's Blaze rocket, with the signature of a soaring rebirth on the breakthrough of the basic principles of physics in a hands-on and practical approach in simulation.
Product specifications. Product name, Phoenix Blaze rocket. Product dimensions, height, approximately 37 centimeters. Diameter, approximately 7 centimeters. Product color, red, orange, gold, and black.
Logistical, material, and functional considerations.
Our group makes sure that Phoenix Blaze rocket will come from accessible, recyclable, and environmental-friendly sources in order to reduce the cost of each material. We considered or prioritized the durability and purpose of our Phoenix Blaze rocket to launch as far and high as possible.
Here are the materials we used for the water rocket and launcher. 1.5 bottle, recycled plastic folder, corrugated cardboard, electrical tape, a little bit of clay, recycled metallic foil, colored papers, pencil, spray paint color block, 2 1/2-inch threaded PVC pipes, 2 small wood planks, ruler, 8 zip ties color black, conduit clamp, nail, and cutter.
Procedure or construction of products. Construction of water rocket.
Prepare the needed materials. Get the two 1.5-liter carbonated bottles. Pick one water bottle and draw a line at the shoulder part of the water bottle. Using scissors, cut a hole along the line. The full bottle goes at the bottom. Take the second bottle that has been cut out, then attach it at the lower part of the full bottle using tape. Add the clay outside the second bottle. Use the folder to create a cone-shaped figure, then attach it securely above the second bottle using tape. Draw a clip delta fin on the corrugated cardboard, then cut it. Attach them at the bottom of the bottle. Once the base of the rocket is done, you may now add the designs and colors that you want to make the rocket more appealing.
Construction of water rocket launcher.
Prepare the needed materials. Get the 2 PVC pipes. Take one pipe and roll it over the candle to heat it up. Once it is soft, push both ends of the pipe and create a bulge which is big enough to fit at the hole of the 1.5-liter bottle. Make a loop of clay and plumbing tape around the pipe where the bulge is located. Then, place 8 equally spaced zip ties around the loop. Once again, place a loop of duct tape but place it over the ends of zip ties. Prepare the end cap and use the drill to make a hole smaller than the tire valve stem. Make sure that the rubber part comes out. Take the unused PVC pipe and put the end cap at the end of the pipe. While on the other end of the second pipe, wrap the pipe tape, then attach the elbow that will connect the first and second pipe. Once the 2 pipes are connected, place it on the wood, then screw the conduit clamp to hold it in place. Then, you are good to go. Launch the product. Here is the theoretical values and solution of our projectile, in which we have disregarded the presence of air resistance. Given theta is equal to 76 degrees, dx is equal to 8.25 meters, T-flight is equal to 2.6 seconds. Required: dx, dy max, vy, vx, T-flight, and v0. Solve first for the initial velocity. Dx is equal to v0 cosine theta t. Input the values and then we will get the answer. V0 is approximately 13.12 meters per second. Next, find the range. Dx is equal to v0 cosine theta t is equal to 13.12 meters per second cosine 76 degrees times 2.6 seconds. Dx is approximately 8.25 meters. To get the time of flight, let us solve for the t peak. Vy is equal to v0 sine theta plus gt. The vertical velocity at the maximum height is 0. Thus, 0 is equal to 13.12 meters per second sine 76 degrees plus negative 9.8 meters per second times time. T peak is approximately 1.30 seconds. For the t flight, we are going to multiply 2 times t peak. 2 times 1.30 seconds is approximately 2.6 seconds. Maximum height. Dy max is equal to v0 sine theta t plus 1/2 gt squared. Dy max is equal to 13.12 meters per second sine 76 degrees times 1.30 seconds plus 1/2 times negative 9.8 meters per second times 1.30 seconds squared. Dy max is approximately 8.27 meters. Velocities on 3 different points of trajectory. Vy is equal to v0 sine theta plus gt is for the vertical component. Vx is equal to v0 cosine theta is for the horizontal component. V at 1 second. Vy is equal to v0 sine theta plus gt. 13.12 meters per second sine 76 degrees plus negative 9.8 meters per second times 1 second. Vy is approximately 2.93 meters per second. V at 1.8 seconds. Vy is equal to v0 sine theta plus gt. 13.12 meters per second sine 76 degrees plus negative 9.8 meters per second times 1.8 seconds. Vy is approximately negative 4.91 meters per second. V at 2 seconds. Vy is equal to v0 sine theta plus gt. 13.12 meters per second sine 76 degrees plus negative 9.8 meters per second times 2 seconds. Vy is approximately negative 6.87 meters per second. Note, for these values, the movement of the rocket is going downwards. For the actual values, we used a stopwatch for the time and a retractable steel tape measure for dx. Actual values. Range. Dx is approximately 8.25 meters. Time of flight. T-flight is approximately 2.6 seconds. Maximum height. Dy max is approximately 8.27 meters. Velocities on 3 different points of trajectory. Vy is approximately 2.93 meters per second at 1 second. Vy is approximately negative 4.91 meters per second at 1.8 seconds. Vy is approximately negative 6.87 meters per second at 2 seconds. Note, for the second and third vertical velocity, the movement of the rocket is going downwards.
We now move on to our motion graph. With the presence of this motion graph, we are reminded that at any point in the trajectory, these velocity components can be identified, and the horizontal component of our projectile motion follows a uniform motion. In other words, it has a constant velocity in any point of this graph. The maximum height of our trajectory is 8.27 meters. The horizontal velocity of our water rocket is 3.17 meters per second as a constant value.
For our vertical velocity at 1 second, the vertical velocity is 2.93 meters per second. And at 1.8 seconds, the vertical velocity is negative 4.91 meters per second. And at 2 seconds, it is at negative 6.7 meters per second, the movement of the rocket going downwards. Vertical velocity changes while horizontal velocity remains constant in many scenarios because of the different forces and dynamics at play in the vertical and horizontal directions. In summary, vertical velocity changes due to the influence of gravity, while horizontal velocity remains constant as long as no horizontal forces, like air resistance or propulsion, are involved. This combination of vertical and horizontal motion is what gives rise to the curved trajectory observed in projectile motion.
Concise explanation about the concept of projectile and loss of motion.
When the water rocket is launched, it follows a parabolic trajectory due to gravity, which pertains to the concept of projectile motion. The water rocket is then launched into the air using the principle of Newton's third law of motion, which is the law of action and reaction. For every action or force, there is an equal and opposite reaction. The action is when you pump the air into the rocket and release it, and the pressurized air forces the water out of the rocket. This creates a force in one direction, which is the backward direction. The reaction according to Newton's third law is that there will be an equal and opposite reaction, so as the water is expelled backwards, there is an equal force in the opposite direction, which propelled the rocket forward.
Till the next launching!